A-level mechanics, adding vectors, triangles of forces. We're going to look at how we can add forces using a vector diagram. If we wish to add several vectors, we can do this by drawing them end to end. For example, suppose we're given three vectors A, B and C, and we want to add them. Well, to do this, we join the vectors end to end. So we start by drawing the vector A. Now where one ends, the next starts. So at the end of A, we draw the vector B. And then, at the end of B, we start the vector C. Now, the resultant of the vectors starts at the beginning of the first and ends at the end of the last. So, we draw the vector A plus B plus C, starting at the beginning of A and ending at the end of C. Now, the order that we add them doesn't matter. In each case, we get the same resultant. So, for example, if we add C plus B plus A, we start with C, where it ends we draw B, and where that ends we draw A. Then we join from the beginning of C to the end of A, and we get the vector C plus B plus A, which is parallel and equal to the vector A plus B plus C, and so the vectors are equal. Now we know that if we have three or more forces in equilibrium, then the resultant is zero. This means the vectors will form a closed polygon with the last vector ending where the first began. Let's have a look at how we can solve a problem by drawing a triangle of forces. In the diagram, the three forces A, B and C are in equilibrium. One is vertical with a magnitude of 147 newtons. The other two are at angles 125 degrees and 155 degrees to it. Find the magnitude of the forces A and C. Well, to solve this, we draw the forces as a triangle. First, we draw the side B vertically down with a length of 147. Then we draw C parallel to the original diagram, and finally we draw A joining the end of C to the beginning of B. Let's label the triangle ABC. We can now calculate the angles in the triangle. If we extend the vector B past A, we get an external angle of 125 degrees, just as in the original diagram, which means the angle in the triangle is 55 degrees. If we now extend the vector C past the point B, we get an external angle of 80 degrees, again as it was in the original diagram. This means that the angle inside the triangle is 100 degrees. And if we extend the vector A beyond C, we get an external angle of 155 degrees, just as we've got in the original diagram. And so the angle in the triangle is 25 degrees. We can now find the missing forces, or sides, using the sine rule. Using the sine rule, we have A over sine A equals B over sine B equals C over sine C. Now we have the angle A is 55 degrees, the side B is 147, and the angle B is 100 degrees. So, A over sine of 55 equals 147 over the sine of 100, and if we multiply both sides by sine 55, we have A is equal to 147 sine 55 over sine 100. And that works out to be A is 122.27 newtons. Now we can also use the sine rule to work out the side C. We've got the angle C is 25 degrees, the side B is 147, and the angle B is 100 degrees. So, C over sine 25 equals 147 over the sine of 100, and if we multiply both sides by sine 25, we get C is equal to 147 sine 25 over sine 100, which works out C is equal to 63.08 newtons. And so we have the force A is equal to 122.3 newtons, and the force C is equal to 63.1 newtons. So when solving statics problems involving forces, this method sometimes has advantages over other methods, such as resolving the forces. It also means that by drawing and measuring a careful diagram, it's possible to get quite reasonable answers without doing any calculations. Example 2. The diagram shows three forces in equilibrium. One is 9.5 newtons, acting vertically down. One is 5.8 newtons, at an angle of 53 degrees above the negative x-axis. And the third is F, at an angle theta with the positive x-axis. In part A, by drawing an accurate sketch and measuring, find the magnitude and direction of the force F. Well, to solve this, we start by drawing a vertical line 9.5 centimeters long. Now, the 5.8 Newton force makes an angle of 53 with the horizontal, so it makes an angle of 37 degrees with the vertical. So we measure an angle of 37 degrees with the vertical, and then draw a line 5.8 centimeters long. We then draw the force F to complete the triangle. Now, using a ruler, we can measure the force F. It's 6.0 centimeters long, so the force is 6.0 newtons. We now want to find the direction of F, so we measure the angle at the top of the triangle. Using a protractor, we see that it's about 35.7 degrees. Now, if we draw in a horizontal line at the beginning of F, we have a right-angled triangle. So we see F makes an angle of 54.3 degrees with the horizontal. And so our answer is the force is 6.0 newtons at an angle theta of 54.3 degrees. Now in part B, from a sketch we're asked to calculate the force F and the angle theta. Well, to solve this, we draw a quick sketch of the triangle of forces. Then, using the cosine rule, a squared equals b squared plus c squared minus 2bc cos a, we have b is equal to 9.5, c is equal to 5.8, and a is 37 degrees. So, f squared is 9.5 squared plus 5.8 squared minus 2 times 9.5 times 5.8 cosine 37. So f squared turns out to be 35.88037, which means f is equal to 5.990022, which rounds off to 6.0. Now we also want to find the angle f makes with the horizontal, so we'll start by working out the angle C. Now we can use the sine rule. Sine A over A equals sine B over B equals sine C over C. And we've got the side C is 5.8, the angle A is 37 degrees, and the side A is 5.99. So, sine of C over 5.8 equals sine of 37 over 5.99. And if we multiply both sides by 5.8, we get sine C is 5.8 sine 37 over 5.99, which means sine C is 0.5827258, and C is the inverse sine of that. So C turns out to be 35.64249, or we can have 180 minus that, 144.35 degrees, although that's far too large, and so our answer is C is 35.64. Now theta is 90 minus c, so it works out to be 54.36 degrees. So we get the force F is 6.0 newtons and theta is 54.4 degrees. So we see our measured answers are very close to our calculated answers. In example 3, we're given a diagram showing two forces acting at a point. In part A, we're asked to draw a triangle of forces to show the resultant. Now to do this, we first draw the 7 Newton force. Then, at an angle of 60 degrees to the 7 Newton force, at its end, we draw the 8 Newton force. We then draw the resultant. And then in part B we're told, hence calculate the magnitude of the resultant. Now we can do this using the cosine rule. The cosine rule states a squared equals b squared plus c squared minus 2bc cos a. And we're given b is equal to 7, c is equal to 8, and a is 120 degrees. So that gives us r squared equals 7 squared plus 8 squared minus 2 times 7 times 8 cosine 120, which works out r squared is 169, or r is 13. So our answer is r equals 13 newtons. Now in part C, we're asked to find the angle the resultant makes with the 7 Newton force. In our diagram, we want to work out the angle theta. And we can use the cosine formula, cosine A equals b squared plus c squared minus a squared, all over 2bc. Now we have the side A is 8, the side B is 7, and the side C is 13. So, the cosine of theta is 7 squared plus 13 squared minus 8 squared, all over 2 times 7 times 13, which works out to be 0.8461538. Now we want the inverse cosine of that. So theta is 32.20423 degrees, or rounding it off, theta is 32.2 degrees. In example 4, we're given a diagram. This shows an object of mass m suspended from a point A by a string AB, and held in position by another string BC. The string AB hangs at a fixed angle alpha with the vertical. The string BC is attached to a movable point C, which is positioned such that the tension in BC is a minimum. BC makes an angle theta with the horizontal. For the tension BC to be a minimum, show that theta is equal to alpha. Well, to solve this, the first thing to do is draw in the forces in the diagram. Now the first one, vertically down, we've got the weight, mg. Then we have the tension in the string AB, and we can call that P. Finally, there's the tension in the string BC, and we can call that T. Now, draw the forces in a triangle. We can first draw in the weight. The force mg has a fixed length and hangs vertically. Now, we don't know the length of the force P, but we know it makes an angle alpha with the vertical. So we can draw an angle alpha. Now the force T joins the lower end of mg with P and is as short as possible. Now the perpendicular distance is the shortest distance. So we can now draw T. And finally, we can also draw P. We can now mark the angle theta And we can see in the triangle that alpha is 90 minus beta. Angles in a triangle add up to 180 degrees. And in the bottom corner of the triangle, we can see theta is 90 minus beta, two angles in a right angle. And so theta is equal to alpha.